Communications between any network devices are divided into layers. For example, if you look at communication from a physical point of view, an example would be changes in voltage levels in a wire. If you look at communication from an application's point of view, for an example, there will be Skype messages transferred from client to server, or HTML pages that are transferred from server to browser. If you look at communication from a router's point of view, there will be IP packets that have source IP addresses and destination IP addresses. The process of communication can be researched from different points of view, and these points are layers of communication. So in my example, I shared with you a physical layer, an application layer, and a network layer. So there are two main models used to describe this communication. The first is the OSI model, or the Open Systems Interconnection model. It's a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system. Its goal is interoperability of diverse communication systems with standard protocols. So the model partitions a communication system into abstract layers. The original version of this model was defined by 7 layers. So even though the OSI model is conceptual, that means it's good for learning networks, but not used directly for real communications. Another model is the TCP/IP model. The Internet Protocol Suite is the computer networking model and set of communication protocols used on the Internet and similar computer networks. It's commonly known as the TCP/IP because these are the most important protocols. You have your transmission control protocol and your Internet protocol, so TCP/IP. These were the first networking protocols defined. So TCP/IP is not only a conceptual model, because TCP, IP, UDP, and other protocols within this model are real protocols that work in each computer. So for understanding Wireshark, that's why we focus on TCP/IP first. These are real-life protocols, and Wireshark can show us the point of view and divide up these TCP and IP layers. So in this slide, you can see both models, the OSI on the left and the TCP/IP on the right. The main thing you should know working with Wireshark is the TCP/IP model. Without it, you're not going to understand what you see in the Wireshark window. So let's describe all 4 layers of this TCP/IP model. First is the network access layer. This is located at the bottom of the TCP/IP suite. This layer allows for devices to communicate within the same local area network, or LAN. One part of the network access layer describes physical parameters of communication. For example, voltage levels in copper wires, or intensity in optical fibers, or connectors, or a number of other wires and cables, etc. Another part of network access layer allows devices to send messages from one to another, but are within the same LAN, or local area network. At this layer, information is contained in frames, so each frame contains a user's payload, their source and destination MAC address, that's the media access control address, and some other fields. The most important protocol that works at this level is Ethernet for LANs, but there's several other protocols you can run as well, such as Wi-Fi. Some devices work only on this layer and not higher, such as a network switch or a hub. For example, if a switch works at the frame network access layer, that means that switch can understand MAC addresses from frame to frame or packet to packet, but can't read IP addresses because there's not IP addresses at this level. They're going to be in the network or internet layer. So the next layer is the internet layer. This is the most popular layer because its main goal is to provide logical addressing and routing. So usually at this layer, the protocol used is IP, Internet Protocol. IP allows us to use logical hierarchy of IP addresses for routing. Every PC can access devices only within its own network, but it has a gateway, which is a router. So routers can have its interface in one network, but the other interface can be in a remote network as pictured. So routers will get IP packets from a PC, analyze it using routing tables, and forward it to the interface which is nearest to the packet's goal or destination. Therefore, at the network access layer, the first layer, we can only communicate MAC addresses within the same LAN or local area network. But At the internet layer, we can communicate between many networks. Next is the transport layer. This provides us with three possibilities. First is reliability. We can use TCP protocol to make a reliable delivery. That means if some packets are lost during transition, TCP automatically resends it. For this purpose, TCP has some fields like SYN, SYN, and ACK, ACK, as a notification method. We can also use UDP instead of TCP. UDP provides unreliable delivery though. It's faster because it has a simpler header, but it's not as reliable. So the second possibility at this layer is tracking individual conversations between applications. We can do this on both source and destination host. So while the internet layer allows us to reach a given host, the transport layer allows us to select the needed application at that host. So TCP and UDP protocols use port numbers for this purpose. So a port is simply a number that falls between 1 and 65535. And these numbers are used to identify an application on a PC. For example, 80 TCP port usually determines a web server. 25 TCP port identifies a mail or SMTP server. The third function of this layer is segmenting. The transport layer can segment big portions of data into smaller segments and transfer them later through the network. Now the fourth and final layer, the application layer. So this is the most common. We all know so many applications, right? Any application such as a web browser, Skype, email client, online games, and so on works at the application layer. The previous layers have identified source and destination nodes as well as applications. Therefore, the purpose of the application layer protocol is for making actual jobs and generating a payload. So example protocols at the application layer level are HTTP, SMTP, FTP, SMB, JPEG, Skype, and millions of others. Payload of any packet capture mostly contains application layer data. The three other layers are used mostly for carrying application layer data. But all the layers work together. Data moves through all the layers from application to network access, and then they move to the destination within the network. Once they arrive at the destination host, the process is reversed, network access level to application. So for an example, a website or HTTP data on an application layer will be divided into small parts, packed into TCP segments at the transport layer. After that, each segment will be packed into the internet layer, IP. Then these packets will be packed into a frame, and these frames will be encoded into voltage levels at the network access layer. Then it is moved to the destination host. So you can visualize the transmission from the application to network access, and then reversing that right back into another person's PC so they can receive that data or website or whatever application. So looking at another example, let's say at the transport layer we get another website or HTTP data. So this adds a transport layer header. This header will include source and destination port numbers and other transport information. After that, the internet layer will encapsulate this segment into an IP packet. And again, it adds the source and destination IP addresses and other necessary IP info to the segment. The packet then encapsulates into a frame at the network access layer level. And here it adds those MAC addresses. Then it moves through the network to the destination host or where it was being sent. Then it decapsulates the data back from frame to packet, from packet to segment, and from segment into the intended application layer data. So for this example, displaying the website data. So encapsulation and decapsulation is necessary for the sending and receiving of data. So Wireshark is simply a network analyzer tool. It's often called a sniffer. It allows you to see the traffic that is received at your PC. Usually a PC receives only traffic that is forwarded to its MAC address. In addition, you can always see broadcast traffic that is directed for everyone in your network. So therefore you can't see other people's traffic, But if a network administrator needs to analyze somebody's traffic, he could configure the switch to send him frames with other destination MAC addresses or other computers within his network. So Wireshark will show you the frames that are received by your PC, and it'll show you all the fields of the layers encapsulated, including all the frames in your LAN or local area network, and the frames directed to your PC. So the first thing you should determine when you open up the Wireshark software is the interface list. It's the first option under capture. It really doesn't matter what kind of interface you choose, Wireshark's going to work the same way. But you should understand you will see frames that are received or sent to this exact interface. I most commonly select the Ethernet interface because it's the main interface, which is also the default for Wireshark. Then just simply click Start to begin your Wireshark capture.